Vector normalization scales a non-zero vector to have a length of 1 while preserving its original direction. For example, given the two-dimensional column vector 3, 4, its unit vector is 3 over 5, 4 over 5. We observe that after normalization, the vector's length becomes 1, but its direction remains unchanged. For this reason, unit vectors are also called direction vectors. The zero vector is usually considered to have no direction, but sometimes it is at the point in all directions. Moreover, when a non-zero two-dimensional vector is normalized, if its initial point is at the origin, its terminal point lies exactly on the unit circle. Clearly, the vectors e1, 1, 0, and e2, 0, 1 are also unit vectors, representing the directions of positive x1 axis and positive x2 axis, respectively. Their terminal points both lie on the unit circle as well. If a vector has a length less than 1, its terminal point lies inside the unit circle. If its length is greater than 1, its terminal point is outside the unit circle. All vectors originating from the origin and having the same length will have their terminal points on the circumference of the circle with that length as its radius. That means if we increase the length of a vector gradually, the terminal point moves along different circles of varying radii, forming a set of concentric circles. This leads us to the topic of vector norms we'll discuss very soon. In a plane, any non-zero vector A can be expressed as the product of its length and a direction vector. For example, vector A, 3, 4, can be written as 5 times its unit vector, 3 over 5, 4 over 5, where 5 is the length of vector A. Furthermore, a non-zero vector in the plane can also be written in the form 5 times unit vector cosine alpha, sine alpha. Alpha is the angle between vector A and the positive horizontal direction. This naturally introduces the concept of polar coordinates. Simply put, polar coordinates define a point's position in a plane using a coordinate system centered at the origin, the pole, and aligned with positive x1 axis, polar axis. The polar coordinate system specifies a given point in the plane by using its radius r and angle theta. Cartesian coordinates and polar coordinates can be converted back and forth. In polar coordinates, the vector corresponding to r theta is r times a direction vector of cosine theta, sine theta. Apparently, its unit vector is cosine theta, sine theta. In three-dimensional Cartesian space, it is easy to determine the direction vector of any non-zero three-dimensional vector. For example, the direction vector of the three-dimensional column vector 2, 3, 6 is 2 over 7, 3 over 7, and 6 over 7. Similarly, the vector 2, 3, 6 can be expressed in the form length times direction vector as well. If the initial point of a three-dimensional unit vector is at the origin, its terminal point lies on the unit sphere. This naturally leads to spherical coordinates. For more details, please refer to the PDF manuscripts and tutor notebooks in the GitHub. In the coming videos, we'll see how unit vectors play an important role in vector dot product, scalar projection, and vector projection.